Hello, my name is Kirti. In last lecture, we discussed Heisenberg's uncertainty principle in detail, and in this class, we will see what is Heisenberg's thought experiment. So, what are thought experiments? So, thought experiments are some kind of logical arguments used by scientists to prove their principles or hypothesis. Okay. So, Heisenberg, he used a thought experiment to prove his uncertainty principle. So, what does uncertainty principle state? It states that it is impossible to know the position and momentum of a quantum mechanical particle simultaneously and accurately. That means if you are trying to determine the position and momentum of a particle at the same point of time simultaneously, then there will be always some error involved in the determination of position and as well in the determination of momentum. Okay. So this error in position is called uncertainty in position and momentum is called uncertainty in momentum. And he also said that the product of uncertainty in position and momentum is greater than or equal to h cross over 2, where h is Planck's constant and h cross is given by h over 2pi. Okay. So this was Heisenberg's uncertainty principle. So now in this class we will see how Heisenberg justified his uncertainty principle using a thought experiment. Okay. So now our aim is to determine the position and momentum of an electron in an atom simultaneously. Simultaneously means together at the same point of time. So this is our atom. So here is our electron. Now our aim is to determine the position of this electron. So since we cannot see through the atom, we cannot use our naked eye to determine the position, right? For this purpose, we employ a microscope. So we use a microscope to look at or to probe the electron in an atom, right? And we know that microscope has a light source. Not all microscopes, but at least the light microscopes will have a light source involved in them. So this will have a light source. Okay, I need to tell you one more thing here. The resolution of a microscope. Resolution means the clarity with which it gives the results or an image. Okay. So the resolution of a microscope is inversely proportional to the wavelength of the light and directly proportional to the frequency of the light used. So if you are using a light source of higher frequency, then you will get a good quality image, okay, or good quality result. But if you are using a light source of higher wavelength or lower energy or lower frequency, you will get resolution of lower clarity, lower resolution, okay. So light source with higher frequency will give you good resolution and light source with lower frequency will give you poor resolution. And now, to determine the position of the electron, you have to incident this electron with the light, right? So now when you incident light radiation on this electron will interact with the light, right? When it interacts with the light, it will scatter some of the light, okay? It will scatter some of the light or photons. Now this scattered photon will be or scattered photons will be detected by this microscope, okay? So this is how you locate the position of an electron. So the scattered photon will give you information about the position of the electron, right? So now if you are using a higher energy light here, what will happen? This electron will absorb the light energy, right? So it also scatters, but at the same time it also absorbs the light energy. When it absorbs the light energy, what happens? Energy of the electron will increase, right? When the energy of the electron increases, then there will be a change in momentum of the electron. So see here what is happening. If you are using a light source of higher energy, this electron will absorb high energy from the light source and there will be a lot of change or increase in the momentum of this electron. But we need to use a higher energy radiation get a good resolution. To locate this electron properly, we need a high energy wavelength, or high energy light. Okay. So when you are using a high energy light, you are ending up increasing the momentum of the electron. So as px changes, delta px, the uncertainty in momentum, delta px will increase. Okay. So if you are using a light of higher energy or frequency, the change, uncertainty in momentum will increase. Okay. Suppose if you do not want a lot of change in momentum of this electron, at that time what will you do? You will use a light wave of lower energy, okay, or higher wavelength. So now what happens when you use a light wave of lower energy? This electron, now it will not absorb a lot of energy from this light, because this light source has less energy. So electron will absorb less amount of energy. That means there will not be a large shift or change in the momentum. So if there is no large change in momentum, then there will be not much uncertainty in the momentum, right? So if you are using light wave of lower energy, you are decreasing this uncertainty in momentum, but this lower wavelength light cannot give you a good information on the position of the electron, right? I already told you the resolution of a microscope, it depends upon the frequency of the light used. Higher the frequency, greater is the resolution. So here in the second case, you are hindering the change in momentum, you are stopping the change in momentum, but you are compromising with the position of the electron. Okay. So when we use light source of higher energy, you can locate the electron properly, but you end up changing the momentum of the electron. So that way delta px increases. You get good value of position, so you get good value of x, accurate value of x, but you will increase delta px. But when you use light wave of lower energy, so this light has low energy, so there will be not much absorption of energy by the electron, so there will be not much change in the momentum of the electron. So the delta px will decrease, but the resolution of the microscope also decreases. That means you cannot locate the electron properly. That means the uncertainty in momentum will increase. Okay. So either way, when you are trying to decrease the uncertainty in one case, the uncertainty in other case increases, right? So if you are trying to locate electron properly by using higher energy wavelength, you end up changing its momentum. And when you try to use lower wavelength, when you try to use lower energy light to restrict the change in momentum, you end up compromising with the location of the electron, right? Or the position of the electron. So you cannot measure both the things simultaneously and accurately. So this is how he justified his uncertainty principle using a thought experiment. So you always have to compromise or trade off between the precision of position and momentum. So from this, one can clearly see that the quantum mechanics, it sets a fundamental limit to the precision with which you can measure the Fourier pair properties like position and momentum, and the same thing also applies to frequency and time and angle and angular momentum. So whenever you try to measure these pair of properties simultaneously, there will always be some uncertainty in each of them. Okay, and whenever you try to particularly focus on measuring one property with 100% accuracy, then you end up increasing the uncertainty in other property to infinity. Okay, so this is how Heisenberg, he justified his principle using this beautiful thought experiment which involves the microscope. Okay, so I hope you enjoyed this class. Thank you so much. See you in the next class.